going to continue talking about energy this week. Now, energy changes in chemical reactions. If we have an exothermic reaction, we're going to have a net release of heat. Think of a campfire burning. An endothermic reaction, energy is added to break the bonds. When you're boiling water, you're adding the energy to break the bonds. So that would be an endothermic reaction. Heat, the energy transfer from an object at high temperature to an object at lower temperature, and it's measured in joules. Now, the amount of heat absorbed or evolved during a reaction is a measure of the energy change that accompanies the reaction. So let's talk about the law of conservation of energy. We've mentioned it before, but let's review it. Energy is neither created nor destroyed in a chemical change. All we're doing is changing from one form to another. We can see the law of conservation of energy in many chemical reactions. And in exothermic reactions, heat is released because the reactants have more energy than the products. In endothermic reactions, we're absorbing heat because the reactants actually have less energy than the products. So if we look at a chart, if we have an exothermic reaction, heat is released. So you'd have your starting reactants, you have your activation energy, and then you have the energy of your products. So here, if this is on an energy diagram, this is your amount of energy, you're releasing heat here. You release energy. But in endothermic reactions, same type thing. You have your reactants, you have your activation energy, and then you have your products. You added energy here. So an energy diagram for your endothermic reactions, your products will have more energy than your reactants. For an exothermic reaction, remember like exoskeleton, exo means out. So the heat goes out of the system. In endothermic reactions, endo is like inside. So endothermic heat is taken into the reaction. So the products of an endothermic reaction will be greater than the energy of the reactants, which is the opposite for the exothermic reactions. Now, the difference in energy between products and reactants in a chemical change is represented by delta H. To find the change in energy in a reaction, we use the equation, the heat of the reaction equals the energy of the products minus the energy of the reactants. Now, it's important to show the states of matter in a chemical equation when you're dealing with energy changes, because energy changes depend on the physical state. So if you are releasing energy, you can guess what state it is, but you don't know if you're going from liquid water to gas or solid to a liquid. So you need to make sure you're showing those states of matter. So here is an example of an exothermic reaction. It's much better than my rudimentary drawing, but you have the energy and the progress of the reaction. You can see that the reactant energy is higher than the product energy because you've released that extra energy into the world. out of the reaction. All that extra energy gets released to the surroundings. An example is methane combustion. So we have methane, we're reacting it with oxygen, we're forming carbon dioxide and water, and we release 802 kilojoules. If this number is negative, the negative number equals energy released because we consider it lost. If it's negative, it's released. If you have a positive energy value, that's energy absorbed because you have to add it. Again, because delta H is negative, it's exothermic. Here, we have an example of an endothermic reaction. Notice that our final energy change is positive. We've gone from liquid to a gas, meaning we added energy, so the products have more energy than the reactants. You can see here the reactants energy is lower than the products. Anytime that happens, energy has to be added to do that. So the products have more energy than the reactants do. Now, exothermic reactions tend to happen spontaneously because it's releasing the energy. It still needs it still needs an activation energy to get the reaction started, but the net change is negative. So it's still releasing more energy than what the activation energy was. Endothermic reactions can be spontaneous, but typically exothermic reactions tend to be spontaneous. Now, we talked about things that affect the rate of reaction, and catalyst was one of them. If we add a catalyst to the reaction, it actually lowers the activation energy, but the overall energy change will remain the same. So scientists have observed two tendencies in nature. One, the tendency for systems to form a higher state of energy to a lower state of energy, which is more stable. That's an exothermic reaction. It goes from a high state of energy to a lower state of energy, from a gas to a liquid, or liquid to a solid. And two, the tendency for systems to become more disordered. That tendency for systems to become more disordered is known as entropy. It takes a lot of work to keep things clean and in order. Think about your room. You could clean your room, but in a matter of minutes, it could be a disaster again. So you have to be conscious about putting things away. The natural state is to just leave things where they are, and it gets messier and messier. That's entropy. Spontaneous reactions tend to occur if energy decreases and if disorder increases. It's not an absolute, but that's the tendency. Now, energy changes in a chemical reaction continued. At room temperature, most exothermic reactions tend to proceed spontaneously forward to favor the products. The energy released is randomly distributed, which increases disorder. And reactions can be spontaneous and endothermic, provided the products do increase in disorder enough to outweigh the added energy. Entropy is that increase in disorder. Okay, practice. I want you to try all of these and then come back and check your answers. Now, a chemical cold pack gets colder when activated. This is an example of what type of reaction. Remember, endothermic reactions need to have heat added. Exothermic reactions release the heat. In an exothermic reaction, the energy of the products is what? So remember, exothermic reactions release heat. So if you have your reactants, and then you have your activation energy, if it releases heat, and this is your energy diagram, if it releases heat, the products need to have less energy than the reactants. So in an exothermic reaction, the energy of the products is less than the energy of the reactants. For question 3, which is an example of an exothermic process? Exothermic is the release of heat, the release of energy. With melting ice, you're adding energy to break those bonds. Boiling water, you're adding energy. Burning wood, you have to add energy to burn the wood. Photosynthesis, or sorry, when you're burning wood, you're actually you're adding heat, but you're getting more energy released. So this one is releasing more energy. And then photosynthesis, you use the sunlight for energy. So this one is also endothermic. But burning wood releases much more energy than that activation energy of added heat to get it going. So you are releasing much more energy than what you are adding in with the burning wood. So that one is your exothermic process. Photosynthesis, you're adding sunlight and you're making the plants are making the energy that they need. All right, we're going to stop there. And we'll see you next time.